All right, so we'll continue our discussion of dynamic programming. All right, so let's consider the following problem: longest increasing sequence problem. So what we have as input is a sequence of n distinct numbers, A1, A2, up to n. What we need to find is the increasing subsequence of longest length. All right. So for example, for this particular input, we have quite a few increasing sequence. For example, this one is increasing sequence of length 5. All right. There are different ones, maybe 2, 3. I don't know want the longest. This one gives a sequence of length 6. All right. So what we need to find is the longest increasing subsequence. That's a problem we need to solve. All right. Okay. So let's see how we can solve the problem. So typically in a dynamic program, we need to define the value because the recurrence relation typically deal with value, but not all the time. But for this instance, we'll define the value. So let's see, we define the value. For each value j, index j, we define the value to be, so define this one to be length ending at particular number. All right, so a particular number, aj, so this one is, say, aj. So for each number, or each position, we define the value. Each position j, we define the value. That's the longest increasing sequence ending at aj. So if we look at this one actually will be 3. Longest one ending here is this one, and this one. So this value, Lj, Lj here. If j is here, so equals 3. For this one, it's 3. So for each position, we have, so this one is 7, right? So L7, here is L7. 1, 2, 3, 4, 5, 6, 7, yeah. All right. So for each position, we will define a number L of the position. All right. So for each value, we have this number, length of longest increasing subsequence ending at aj. All right. Now, what's our answer in terms of this definition? What is our answer? The final answer, because this number needs to be related to our answer, otherwise no use, right? So our answer, or our solution, exactly, it's maximum. Okay, so solution is maximum. Later on we'll see actually we can get rid of this one, but for the time being, so it's really solution of this one. It's maximum of Lj, right? All right, so it's related, so this value is useful. Now we try to find the recurrence relation for this value. Okay. So the recurrence relation it's very easy to obtain. We consider all numbers that appear before aj and which is less than aj. So the then length will be maximum length of this ai plus 1, position I plus 1. Okay, So illustrate it. Let's illustrate it. So here at AJ. Okay, sorry. Yeah, the pen, this pen does not work very well. Sometimes it does. Or like sometimes. Okay. So we consider all number appear before this number AJ, and which smaller than AJ. So maybe these three positions maybe. Okay. So they are smaller. So maybe let's put the actual number in here. Okay. So, let me just say AJ here. So this number may be 10. So this one may be 8. That's maybe 5. This one is say 4. All right. So maximum length will be one of them plus 1. So it depends on which one is bigger. So it's now we can see if we draw arrows from these 3 numbers to this one. What do we get? Actually, we see a DAG. That's underlining DAG. All right. But anyway, the current relation is obtained in this way. Look at numbers appear earlier and smaller than AJ. Then the length will be 1 plus maximum length of these 3, these numbers. All right. So we get to the current relation. All right. Now the remaining question, how do we compute this recurrence relation? Now here is where the DAG comes from. In order to compute this relation, what do we need? The key point is when we compute LJ, these are computed already. So all these values should be computed already. That's a key requirement. Otherwise, there will overlapping problems, so that we lose efficiency. All right. So that's a key requirement. So how can we ensure that we can compute this value LJ in such a way that this key requirement is satisfied? So here is where the DAG comes from, the underlying structure DAG. All right. So let's consider this particular example. Let me erase something here. Okay. Actually, it will be easier. I copy the numbers and instead of erasing it. I think it's easier to do it in this way. Okay, so this example. Yeah, it's faster. Okay. All right. Now we look at the dependency of how we compute L of J. So what value will be required when we compute L of J? Say, for example, this 9. Sorry. This 9. We look at dependency. Oh, that's 9 maybe too big, too many. I consider something smaller, maybe 6. Okay. So we need this one, and this one. So we draw a dependency graph. So arrow will pointing from these nodes to this node, or these vertices to this vertex. So for each vertex, so we regard each number as a vertex. For each vertex, we add edges in this way. So for this 4, so let me use a different, I use same color, okay. For this 4, so dependency will from 2 to 4 and from 3 to 4. All right. So what we get? Here we get a DAG. For this particular problem, the graph we obtain, if we draw this diagram, what we get is a DAG. All right. Now we use this DAG. So actually, in this particular case, this linear ordering is already a topological sorting, a topological sort, or topological ordering of this DAG. So what we can do is just follow this ordering to compute Lj in this fashion. So that's bottom-up manner. All right. Okay. So that's how it's computed. So in terms of DAG, what do we compute for this DAG? Actually, what problem do we solve for this DAG? For this red DAG? If we use the same recurrence to solve the problem for this DAG, actually what Lj means for this DAG, for this red DAG? What's the meaning of this one? Do you see it? It's a path problem. Actually, we compute, yes, length of longest path. We compute the length of longest path. We solve longest path problem in a DAG. In general, the problem is very difficult, but in a DAG, we can solve the longest path problem in linear time by using this recurrence. Of course, in general, if the DAG is weighted, then here is not 1. It will be changed to weight. All right. So actually, it should be put inside. So longest path. Say longest path. So now let's discuss longest path. Actually, this one does not work. Need to be changed. We cannot just simply say weight plus this one. So now we see how we solve longest path problem in a DAG. All right. So actually, it's Vj equals maximum. The translation is LVI plus weight of edge VI Vj. So here is VI Vj in an edge. So that's the translation we use to solve the longest path problem in a DAG. Again, using the underlying DAG, we compute this one from left to right, following topological ordering of the DAG. All right, you see, it's quite simple, right? Once we have the DAG, actually it's very simple. We just visit vertices in the DAG from left to right and compute the function from according to this ordering. So that's bottom-up fashion. All right. You can say length 1 or length 2. This is differ by 1, does not matter. This small technical point depends on how you define it. Okay. Otherwise, it's just differ by 1. So if we count the number of edges or number of vertices, all right. Yeah, that's small technical issue. All right. Now, for the longest subsequence problem, we know the relation between the solution and Lj, individual Lj, is maximum of all Ljs, right? But actually, we can get rid of that, just become a longest path starting from a single vertex. So if you don't like that relation, so previously we have this, our solution for longest increasing sequence, subsequence, a solution equals maximum of Lj or Li, does not matter, okay? If you don't look like this, if you don't like this one, you want some kind of single thing. So it's very easy that we can do this. Add one vertex, or add one number in the front. So here add 0 in the front. So then it's become a longest subsequence starting from this one, starting from this number. So in terms of longest path, it become longest path starting from a given vertex S. Okay, then we don't need to have this relation. Of course, here in longest sequence, increasing sequence, it will be differed by 1. Okay, all right, clear? So get the basic idea of dynamic programming and underlining DAG. So DAG, the underlying DAG really tell us how to compute the recurrence from bottom-up fashion. All right. Okay, so let me give you 2 more examples today. I think I have time for these 2 examples. One is related to homework problem. But for homework, you should not do it in this way. Do not use dynamic programming. All right. Otherwise, I told you solution already. All right. A shorted path with at most k edges. All right. So this problem, in a graph, we want to find the shortest path. So let's again use maybe diagram. Okay. This vertex, call it S. Maybe let's put weight. So maybe 2, 3. Here maybe 4. All right. Now, shortest path from S to this vertex T, of course, it's easy to see. It's of length 3. Everyone see it, right? But now I have a restriction of number of edges I can use. If I can use at most 2 edges, since this one is not a legal one, we cannot use this one. Since shortest path with at most 2 edges is not 3. The length is not 3, but rather it's 5, is this one. So that's a problem. Actually, it's a homework problem. All right, I believe, let me check. Homework. I think, which one? Let's see. Yeah, 4.10 at most k edges. Set homework problem. But don't use this solution for your homework problem, okay? Otherwise, cheating. All right, so how can we solve this problem using dynamic programming? So we're going to solve this problem using dynamic programming. All right. So what do? We need to define the values that will be used to define the recurrence relation. So here value will be depend on 2 things. One is the distance, another is number of edges. So it will be involve 2 variables. So we use dvi to denote length of shortest SV path under the restriction with at most k edges. Okay, so here shortest path is the SV path, of course. All right, find the path from S to vertex V. All right, so we define it in this way. Now what we need to do is obtain the recurrence relation for this value. So again, it's very simple for shortest path from vertex V. In order to get to vertex V, of course, we consider all its in neighbors of V. So any path had to go through these vertices, right? All in neighbors. Sorry. All right. So then dvi use at most k edges. So for these vertices, we're allowed to use at most I minus 1 edges. So here it's use I edges. And for these vertices, all these vertices, number of edges can use is I minus 1. Right? Because I use 1 more edge after that. So this one will be minimum 1 for all these vertices. Okay, so d u I minus 1 plus w u v. All right. Or I have v, I use I minus 1 edges to v. So only these possibility. All right, because it says at most k edges. So maybe here I is less than I. So this one needs to be included. All right. So we get this reconciliation. All right. So once we get this reconciliation, then it's possible to use dynamic programming if we have an underlying DAG. Does this one have underlying DAG? Underlying DAG for DVI. So actually this one is look like a two-dimensional table. All right, so I here I and D, I equal 1, 2, 3 up to K. So here are vertices. All right. So dependency, this one is depends on laws above it. No, you cannot use dynamic programming for that homework problem. Okay, otherwise you are cheating. All right. No, I'm not. There's no point to solve the problem using this one. I told you how to solve it. You have to use a different approach. Okay. Not dynamic programming for the homework. All right. No, so this one dependent in this way. So if we all the vertices, all the vertices of this stack, so first row, we put first all these vertices first, then follow the vertices of second row. Please don't ask this kind of questions. Okay. Final, there's nothing to do with final here. We're discussing dynamic programming. Then, so first row followed by second row, and so on. So that's all topological ordering of the deck. So following this ordering, we'll be able to compute this one without overlapping things in a bottom-up fashion. All right. Okay. So again, you see the underlying deck, and that's really plays a key role in dynamic programming. So that's what enable us to solve this problem using dynamic programming, because we can compute things in bottom-up fashion. All right, so let me go back to idea for dynamic program. Typically, it involves 4 steps. We discussed the 3 already. The other step will be discussed on Thursday, I think. No time today. Oh, sorry. Yeah. The question asked not for particular homework. You mean the style of homework to solving homework problem. Typically, you need to give reconciliation. Then the bottom-up part, you need to write pseudocode for the bottom-up part. Okay. Typically, you need to do that. Unless, like for me, for journal paper, sometimes I would just say it's standard. I give a reconciliation that I will say just it's standard use bottom-up fashion if it's quite obvious. Otherwise, I need to write pseudocode. All right, to answer your question. Okay, sorry, I misunderstood your question. I thought you referred to that particular problem. All right, now 4 key steps in designing a dynamic programming algorithm. Okay. There are 2 different books. There may be different style. Okay, depends. First, Typically, dynamic programming is used to solve optimization problems. Typically for optimization problems. All right, so typically we want to compute the value, maximize value or minimize the value. So it's typically for optimization problems. So 4 key steps. So typically this first step is the value we need to obtain. All right, then maybe like A, B, 1, 2, 3, 4 instead of A, B, C, D. So let me summarize this one again. So that's where the dagger comes from. All right. Now, so these will only allow us to compute the value, but the actual solution actually does not give us. So typically, in order to compute the actual solution, there are one thing that is involved. So we do some bookkeeping the process, which we have not discussed yet. But actually, you have seen it in Dijkstra algorithm for computing shortest path. So this is the fourth step we'll discuss on Thursday. I don't think we have time today. All right. Okay, so typically that will involve 4 steps. Yeah, going back to the final example, in case we have say final exam, we have a problem on dynamic program. Typically, I will tell you what to do. So maybe just 1, 2, 3, 4, ask you to do these 4 things. So to make things clear. So then to avoid misunderstanding. All right. Okay. So typically that's what happens in dynamic programming. And as I said, typically dynamic programming is to solve optimization problems, but it is not always so. So I will give you a problem that nothing to do with optimization. So in the homework, I will ask you to solve optimization problems related to this problem, which is called the subset sum problem, which is very, very important. All right. It's related to homework problem. All right. So I give you a set of numbers, say positive integers. So S set of positive integers. All right, and give another integer n, big N integer. Of course, it's positive. So my question is there a subset inside S whose sum, such that whose sum equals exactly n? So that's a problem we needed to solve. So that's not an optimization problem. I need to find a subset with certain property. All right. So the answer will be yes and no. But actually, in practice, of course, you need to find the actual subset whose sum equals n. So for example, So suppose I give you this set S. Actually, the problem is very difficult to solve. So for example, I want to know if there exists a subset in this example whose sum exactly equals say 101. So that's the question. Anyone find a solution? I have no idea whether there's that or not. Yeah, actually I found one. Greedy does not work. Of course not. Actually it has a solution. It's not easy, but I think I'm just lucky. I think it has a solution. This one is a solution. So I happen to be lucky. I just by observation I found one, but actually it's very difficult. So how can we find such a subset? One way is greedy does not work. Largest element first, of course, does not work. One way is try our possibility, try our subsets. Of course, but then there are this many subsets. It's exponential time, right? It's very slow, does not work. In general, we don't have a polynomial time algorithm at all because this problem is very hard. It's called NP complete. But when n is small, usually n is not too large. Then we can have algorithm depending on n. It's not a polynomial time algorithm, but in practice, it's very useful when n is small. So now we're going to design dynamic programming algorithm to solve this problem that will be very useful in practice when n is relatively small. It's not too big when this n. All right. So here again, we need to define the value to see how it's related to solution of the problem. So here it's nothing to do with optimization. So the question in the homework, I forgot. Last problem, I think. Let me check again. Homework problem. Yeah, last one. It's related to it's basically this one, but then not only find the set, but actually the size of set should be minimized. Okay. Now here dynamic programming with memorization does not help. I will discuss memorization later on Thursday as well. All right. Now what we do is we define the value. So first let's put things in order. So let's organize things. So S will be just denoted by n numbers, say S1, S2, order these elements. A set is not ordered, but now we order them. So the names will be S1 to Sn. All right. So then define the value depending on two values, I and j, ti and j. And the meaning is this one is choose value of the statement. This one is a very good template for many problems. So that's why I want to discuss it. The first n elements, first I elements. First I elements, okay, contains a subset whose sum exactly equal j. This pen does not work very well. It's kind of random. Sometimes work very well. Suddenly it does not. All right. So this value depends on two things. One is I, one is j, and the value is either true or false. So two values, of 1 or 0. All right. So meaning is the choose value of statement. The first I elements contain a subset whose sum exactly equal j. All right. So how does this value relate to our solution? So we look at the special case that is T n bigger n. This one equal 2 if only if it has a solution. Otherwise, it has no solution, right? So that's how it's related. So next thing we need to do is to have a recurrence relation for this one. Okay, so what's the recurrence relation for this one? Of course, there are boundary case. Let's discuss the general case first, then come back to boundary case. We want to get recurrence relation between Tij and Ti prime J prime when I prime is less than or equal to I prime and J prime is less than or equal to J. So that's the purpose, to find the relation between this one and the small I and J's. All right. So let's look at this one. So first, I elements. Now, for any subset of solution, just consider this particular element. There are two possibilities. Either contain this one or do not contain this one. Do not contain this one. Any solution of this one, there are only two possibilities. Either contain it or do not contain it, right? So if it does not contain this one, what happens? If it does not contain this one, give us this. Then solution comes from the first I minus one elements on the first I minus one integers. All right. So if it does not contain it, then we have Ti minus 1, J equal 1. No, we don't compute our subsets. Okay, dynamic programming is no, even all subsets whose sum less than n, no, because elements are ordered. Some we do not compute them. Now, if you do it in this way, it's not good. All right. So you really need to spend a lot of time in order to really to understand essence in dynamic programming. It's exhaustive search, but exhaustive search in a clever way. Otherwise, we will not be good. It will not be good enough to reduce the search space enough in order to make an efficient algorithm. All right. But anyway, let's focus on the recurrence first. So if it does not contain this particular element Si, we have this one. Otherwise, the case, so we can ignore this case. So this case has been done. It contains Si. When it can contain Si, so the value of Si should not be too large, should not be more than J. If it's more than J, we cannot include it. So Si must be at most J. All right. And let's see, not enough space here. Sorry, let me try. Okay. Let's see. So, it's look awkward. Maybe I rewrite it. A space. I leave more space here. Otherwise, it look awkward when I put this one down. Okay, so two cases. So one is this particular element Si is not inside the solution. We have this one. And then it's inside the solution. We have this one. So this means Si belong to solution. So here Si does not belong to solution. All right, two possibility. So when it does not belong to solution, it's easier, just one statement. Otherwise, Si must be no more than J. We can include it. So after included, the sum will be reduced. So here sum is reduced. All right. Okay, so get the reconciliation. So once we have the reconciliation, less is simple. We just say the underlying DAG and we use that to do it in bottom-up fashion. But before that, we need to check the boundary condition. Every reconciliation must have a boundary condition. That's very important. So I did not discuss it for everyone, but it's very, very important. Each of them has a boundary condition. Otherwise, result will be totally different. All right. So for this particular reconciliation, the boundary condition is the I equal 1, the first element. So we just consider the first element. When does this one equal 1? Of course, if J equals S1, we just take S1. But there's another case. No. If we want sum to be 0, so J equals 0. That's a special case. In this case, we do not take element. Then summation is 0. So don't forget this part. It's very easy to forget this one. And when you implement the program, then you will see mistakes. So this one is easy to see. You will not forget this one. This one will be included. But it's easy to forget this special case. All right. So that's boundary condition. So these two together give us reconciliation. All right. Then again, it's a two-dimensional table. So all these values are all integer positive integers. Okay. If negative, I have a question for you. If there are negative integers, then what do we do? All right. So here's ij. It's a two-dimensional table. All right. Now the value, any particular Tij come from dependence, only two come from the previous low, from ith low, because you see I minus 1, I minus 1. All right. So that means this digraph is a dead. This digraph, dependent digraph is dead because we can add elements, the first low, second low, and nth low. So if we add these vertices from left to right in this way, so all vertices first low, all vertices second low, and so on, you will see all edges goes from left to right. All edge goes from left to right. So it's a deck. All right. So therefore, we can compute the whole table in this manner, use bottom-up fashion. Bottom-up fashion. All right. Total time it takes is n times big N. That's the time it takes. No, the path is does not represent a subset. Oh yeah, sorry, you mean the path in the deck? Yeah, it's corresponding to a subset. Yes, it corresponding to a subset. Okay, actually, let's give you a big hint for the homework problem. Okay, last problem. All right, so this time, the final thing I want to mention, that it's not a polynomial time algorithm. So it's a polynomial in terms of n, number of elements, but this part This part is exponential because it's the length, input size. Input size is n plus log n. So this part, encoding of n, big N, is only log n, but n is exponential function. N is exponential of log n. So it is not really a polynomial time algorithm. So for small n, it works very fast. But when n is large, then it's slow. And it's theoretically, it's not a polynomial time algorithm because of this n. So encoding is only log n. The length is only log n. But here the complexity is n. All right. Okay, the pseudocode is in the notes. I'm not to go over it. It's quite simple, but you need to be careful. Just select the translation of the recurrence relation. And on Thursday, we'll continue discussion on dynamic programming. And I'll give you 2 more examples, I think. Then I will discuss step 4 and also machine memorization, another way to compute the value from top-down fashion instead of a bottom-up fashion. All right, but in practice, usually we use bottom-up fashion in terms of efficiency, because top-down fashion has overheads in recurrence calls. All right, I think this time up, and I will stop. We'll continue on Thursday. All right. Okay. Any questions? Yeah, please think about dictionary algorithm. How does it fit into dynamic programming? I will discuss it on Thursday. I will mention it on Thursday. Okay, so when we discuss dictionary algorithm, we say it's a greedy algorithm, but actually we can also view it as dynamic programming. Oh yeah. Okay, are you in terms of weight? No, you refer to longest increasing subsequence. No, the path weight is not. It's only 2. It's 2. It's sorry, only 1. If you look in terms of number of edges, only 1. All right.